Hello everyone, this is Dr. Hira. Today we will discuss about carboxylic acids and their derivatives, but our main focus of this lecture is how we can name the carboxylic acid. So we will discuss more about the carboxylic acid. So carboxylic acid is one of the major class of organic compound, and there are a number of drugs in medicine which you are using commonly in your daily life as a painkiller, as an anti-inflammatory drugs. So they are based on the carboxylic acids or their derivatives. So I have in the slide you can see Advil and Tylenol, one of the most famous painkiller drugs, and in our local pharmacies we also know the very famous drug which is the Panadol. So these are the drugs which are available with different trade names, but they have the different chemical formulas, and some of the drugs have the different trade names, but the chemical formula is the same. So here is example is ibuprofen. So this is the chemical structure, and if you just look at this one, this is isobutylphenyl propanoic acid. So this is the carboxylic side, and this is the acidic group, and we have the different substitution on it. So the common name is ibuprofen, and its IUPAC name is isobutylphenyl propanoic acid, and the trade name with which different pharmaceutical companies or pharmaceutics are available. So this is Advil, paracetamol, and aspirin. Now, in aspirin, we have the acetyl salicylic acid, but the reason to mention it here is this is also an carboxylic acid based drug. Another one is acetaminophen. So here you can see directly the carboxylate group as such, but this is the derivative of the carboxylic acid, and this is um, available in a market with the name of Tylenol and the Panadol. So Advil and Tylenol are two most common and very famous brands which are available in the United States and internationally in other countries too. And in our local market, we have the paracetamols and the Panadol acid. So the slide is basically to represent you the application of the carboxylic acid, that how much is the importance not only in the drugs, but they are also very useful in our food industry, number of different industries, and most of the common example is acetic acid, which is available in your kitchen. So now we will move about discuss about the structure of the carboxylic acid. So with our previous discussion about aldehyde and ketones, so if you want to refer to these relevant lectures, so you wanted to know about more about the carbonyl compounds, so you can watch my other lectures on the aldehydes and ketones and the carbonyl containing compounds. So where we have discussed generally that what are the different carbon containing compounds. So the functional group of carboxylic acid, which is another class of organic compound, is the carboxylic group. So why we say this as a carboxylic group? So this is basically the derivation, and we have extracted these words from the two terminologies. One is the carbonyl, and the carb is extracted from the carbonyl, and there is the hydroxyl group. So oxyl is extracted from that functionality. So the generic formula of any of the carboxylic acid is the carbonyl, C double bonded O, and this is linked with the hydroxyl group. So that's why this class is known as a carboxyl, because this is having the carboxyl group, and because they are acidic in nature, so that's why we also add the acid with that one. So these is the carboxylic acid class. So they could be aliphatic and they could be the aromatic one. So for the aliphatic carboxylic acid, the general formula is RCOOH. So R is for any alkyl group. That could be methyl, ethyl, pentyl, hexyl, anyone. And the AR1, aryl, is basically any of the aromatic or benzene based compounds. So these will be the aromatic carboxylic acid. So here in these structures, I have written the condensed structure of the carboxylate, that how you can write the carboxylic group. So CO2H, if you wanted to shorten that structure. So that bonding is just showing that it is linked with some of the other group or a chain. So that could be R, any alkyl, that could be any aromatic one. Or you can write it as COOH, but don't forget that this oxygen is attached to the carbon in the form of the carbonyl. This is the C double bonded O, and then there is the OH group. So this is the line and an open structure, line structure of the carboxylic group. And this is the Lewis structure where we are mentioning the lone pair of electrons also, where there is the non-bonding electrons are available. So these are the different representations of the carboxylic group, how you can write that one. Now we will come to the IUPAC naming of carboxylic acids. So mostly the rules are the same, as we can name the alkanes or any other of the class regarding the which chain we have to select. But obviously with the class, each class, we have to consider some of their special rules which linked how we can name these compounds in terms of what specific suffix we will use, and from which side we can start the numbering the longest chain. So in case of the carboxylic acid, you have to choose the longest chain that contain carboxylic group. So don't forget that in case of the alkanes, where we don't have any of the functional group as such, so this was all make of the carbon and the hydrogen. So there we were considering the longest chain if there is no substitution. So any side is equivalent. But if there was any of the substitution, so then we prefer the side where there are the more or higher number of the substitutions, right? So any of the other class, we follow these similar kind of rules. And of course, in the carboxylic acid, because the carboxylate or the carboxyl group is the major functional group, so that will determine it as a major class. And do remember that the carboxyl group has the preference over other functional groups like the hydroxyl amino. I will talk about these in the next slides. So we have to start, or we have to count, or we have to select the longest chain which contain that carboxyl group, right? So we can't ignore that major functional group and then we can choose something else. So we have to pick that longest chain which include that carboxylic group. Now we will start the numbering from the side where there is the carboxylic side is attached, as we used to do in alkene and alkyne, where there is a double and a triple bond. So because that is the distinct functionality, so we start number the chain from the side where there is the uh, double or a triple bond position, and we can assign the lowest number to that major functionality side. So here in carboxyl, the carboxyl group, carboxylic acids, the carboxyl group is a major functionality. So we will start numbering the chain from this side. Another interesting point, which is not like the alkyl halides or other compounds. So here, this carbon, so this is all the same as we did with aldehyde and ketone. So you can see the naming of the aldehyde and ketone if you want to discuss more in work on the carbonyl containing compounds in detail. So I have a lecture on the naming of aldehyde and ketone, so you can go to that lecture too. So the carbonyl carbon is also included in the longest chain. So we will not count the longest chain excluding this carbonyl. So what I mean is that if you just look at this chain, so there could be the one chain 1, 2, 3. This could be the longest chain. There could be another option 1, 2, 3, 4, right? So this is basically the longest chain. So from where I have to start the numbering the chain is this one, to assign the lowest number to the major functional group. So 1, 2, 3, 4, or 1, 2, 3, 4. So any of the side I can choose here, right? So let's say to elaborate more for you. So this is the longest side chain which we are selecting here, right? So number 1 will be this one. This is the 2. This is the 3, right? And this is the 4. So how we can name that one? So I have told you that the suffix we will use is oic, oic, and acid. So we will write it with the space. So this is not a single word. So the parent chain name, then space, then there will be the acid one. So this is the simplest carboxylic acid with only one carbon, and this is the formic acid. It's its common name, and IUPAC name is methanoic acid because this is only having the one methyl group. So next is the ethanoic acid, because ethane, if we will just write ethane, so it has the E at the end. So we have to remove that E, we have to replace that E from the name of the parent alkene and adding the suffix oic and the acid. So this is the ethanoic acid, and its common name is acetic acid. Now the third one is, if you just count it, 1, 2, 3. So at the third position, there is the substitution, and this substitution is the methyl group. So 3 methyl, and what is the longest chain? So this is the 4 carbon chain. So for this, we will use the butane, and oic acid is to represent this carboxyl side, that this is the carboxylic acid. And its common name is isovaleric acid. Another interesting point about the carboxylic acid, which needs to emphasize, is that they are mostly, most of their common name are IUPAC accepted. So don't wonder if you see more in literature the formic acid and acetic acid in place of their IUPAC name. So they are, IUPAC has accepted their common name also. So they are frequently used. So unless we are asked for writing the IUPAC name, so you can write its common name as well. But of course, from the IUPAC name, we are able to accurately get the idea at what its structure is. Either that is a 1 carbon chain, either that is 2 carbon chain, so that we can draw its structure rightly. Now the third point is that in case we have the substitution as we did here in the third example, so we will find out its position of the substitution and the name as we did in the alkenes. So we find out that this is the third carbon on which the methyl group is attached. So simply we have added it, the 3 dash methyl, and the rest is the butanoic acid for its fix and its chain name, the parent chain name. Now there are the carboxylic acids which have the double or the triple bond. So what we will do, how we can write its IUPAC name is, so then we have to change the ene with ene and yn. If there is a double bond, so we will write the butanoic acid, and if there is a triple bond, so butynoic acid. So we will do some practice in our next slide. So now the IUPAC name of some of the carboxylic acids. So here I have given the example of the aliphatic carboxylic acids and aromatic carboxylic acid. So if you just look at the first example, this is the 1, 2, and 3, right? So this is the 3 carbon structure. So for this, we will use the prop, right? Now, this is not the alkane. So there is the double bond. So for double bond, we will replace the AN with the EN, right? So this is the propene, and oic acid is to represent that this is having the carboxylic group. Now, what is the position of the double bond? So the position of the double bond is that this is between the carbon second and the carbon third. So we will write the lowest number from the first carbon from which the double bond is started. So the 2-propanoic acid, it's IUPAC. You can write prop 2 enoic acid. This is equivalently right. So there is no problem with any of that name. So you can choose any, you can pick any of that. Acrylic acid is its common name, and you know that acrylic acid is one of the very important and common raw material for our synthetic material and most of our fabric plastic industries. Now, the second compound is the 1, 2, 3, 4. So this is the 4 carbon chain. And for this, we will use the bute. Now the double bond is between 2 and 3 carbon. So this is bute 2 enoic acid, or we can write the trans 2 butanoic acid. As this was the simplest example, so there was no other possibility where that double bond can be placed. So there is no cis and trans conformation because this is not having any of the other R group here, right? So in case we have the chiral center, so we will see that either the both bulky groups are on the same side or in the opposite side. So trans means that the chiral carbon and these both basically the carbon which are doubly bonded attached to each other, and they are bonded with the two different groups. One is the lighter and one other one is the heavier one. So where this is not mentioned, so there is basically the hydrogen. So I can write for you so you can understand that. So basically this is carbon, right? This is doubly bonded with another carbon, and there is the CH3. So this carbon also has one hydrogen here, right? And same is for this. So if you just look at this one, now these two carbons which is doubly attached to each other. So there is a CH3, there is H, there is H, and there is this carboxyl side. So if you just compare that they both lighter atoms are in opposite to each other. So that's why they are trans. So in common terminology, we can write the trans, but in EZ stereochemistry terminology, you can conformation, you can write the E. E is for anticoagulant. So this means that is opposite. So the both bulky or the both lighter are not sharing the same plane, right? So the lighter is upward and here the lighter is downward. We have discussed, and I will plan a lecture on the stereo chemistry and on E and Z conformation also. But I hope you have that idea that how we can write the E and trans. So along the double bonded carbon, we have to see that where the lighter atoms are facing. So if they are facing the same plane, so we will write these as Z, and if they are sharing the opposite plane, so they are the E and again. And in that terminology, if they are sharing the same plane, so that will be the cis, otherwise that is trans. So now we will have another example. And here we have this aromatic one. So it's, if you right now you just forget about this confirmation, firstly we will just go for the naming. So this is the 1, 2, 3. This is the 3 carbon chain which is aliphatic, and there is one benzene which in connection we write as a phenyl group, right? So this phenyl is attached at the 3rd carbon. So 3 phenyl and propanoic acid. So obviously we need to, though this is understood that this double bonded bond will be there if that is the benzene ring here and there is a carbonyl, but if you want it for the more clarity, so you have to write the position of this double bond also. So this is the 3 phenyl 2-propanoic acid, and its common name is cinnamic acid. And the cinnamic acid derivatives and its ester, they are present in our cinnamon sticks we use in our most of our dishes, right? So you can smell their smell from the smell. You can say that these are just like the cinnamon stick smell. So E, again, this is in the transposition. They both are in the opposite, and that's why we are writing it in a bracket E. Now we will see another other rules and how we can name that one. So if we have the other substitution on the carboxylic acid, so how we can name that one? I have told you that the carboxylic group has the first preference among all of the functional group, and the halogen has the least preference from the major functional group, excluding the double and the triple bonds. So here they will get the preference either if we have the hydroxyl, if we have the amino group, if there is any of the carbonyl compound. So what are the prefixes we will use? So why we will use a prefix? Because I have told you that an IUPAC name, there are the three parts of the organic compound. One is the parent, prefix, parent name, and then there is the suffix. So I can write it here, parent, so that maybe not written very well, but you should know this is the prefix, right? And there is the suffix. So a name contain usually these three parts. So suffix will give you the idea about the class of the compound, right? So the parent is giving you the length of the chain length, right? So prefix give you the information about the position and the name of the substitution. So if we have the hydroxyl substitution on or carboxylic acid, so what we will use is for hydroxyl, we will OH group, we will use the hydroxy as a prefix. If we have the amino NH2 group here, so we will use amino as a prefix. If there is a carbonyl C double bond O, then we will use, for example, aldehyde and ketone. And then we use the oxo, because carboxylic acid could be the combination that it has the other polyfunctional, that it has more than one functionality. So how we will treat the other functionality. So here you can see this is the OH group which is attached. So how we can name that? Firstly, we have to locate the first longest chain which contain the carboxyl group, because this is the major functional group. So 1, 2, 3, 4, 5, and 6. So this is the fifth position where the OH group is attached. So for OH, we will write hydroxy. So this is the 5-hydroxy, and this is the 6-membered chain, including this carbonyl carbon. So this is the hexanoic acid. And now we have written the R, because there is no double bond. This is the alkane, and there is a chiral carbon. And for this, we used R and S, sinister and rectus, right? R and S configuration. So this chiral carbon, we will see that either this priority order is counterclockwise or clockwise. If this is the counterclockwise, then we will write S. If this is clockwise, then we will write the R. So I will show you that how this is the R. So for the chiral carbon, this is a chiral carbon, and it has the one hydrogen, which is understood, right? So because in a line structure, we're not mentioning here. So this is the fourth, because I use the highest preference with the higher number, but you can use the representation that you assign it the lowest number. But for me, that is more convenient. So you can just follow that pattern. So this is the 4, because this is having the higher priority, because this oxygen has the highest atomic weight among this carbon and hydrogen. Now this is a 4, this is a 3, the whole side of this one, and this is the second, and this was the 1, and the hydrogen you always put at the back side, so just to uh, uh, keep it as a reference and holding the molecule, and then we will decide where the priority arrow, so preference is moving if we plot the arrow in the direction from higher to lower. So this is the higher to lower, and if I just put that arrow, so this is basically in the direction of the clock motion. So this is the clockwise motion. So that's why we write R here, right? I hope you get that idea. So now the next one is with the carbonyl. So for carbonyl, again, this is 1, 2, 3, 4, 5, fifth position. This is a carbonyl. So we will write this oxygen as an oxo. So 5-oxo hexanoic acid. Now the third example is with the NH2 group, and here you will see 1, 2, 3, 4. This is the 4 carbon chain. So for this we will write the butane and oic acid for mentioning the carboxyl group. And because this understood that that carboxyl group is sharing the one of the extreme that cannot be within or at the middle of the molecule, so this is sharing the one end of the molecule, so this always assign the 1 number, so then there is no need to mention that one. So 1, 2, 3, and 4. So this is the fourth position where this NH2 group is attached. So this is a 4-amino butanoic acid. So I hope you get that idea. So now the next thing is that there are a number of carboxylic acid which have more than one carboxylic acid or carboxyl side. So how we can name that? So you will simply use the suffix dioic acid or trioic acid, depending on how many carboxyl side they are sharing, right? So usually they are only in the dioic acid, dicarboxyl side. So we will write it as a dioic acid at the end of the name as a suffix. So these are 5 of the most famous dioic acid which we use in our teaching lab and most of our synthetic and research chemicals. So you are familiar with these one. So maybe you are familiar more with their common name, and now you will today you will be able to know their IUPAC name as well, or maybe vice versa. So here this is the ethane dioic acid. So the one easiest way to remember these 5 is the OMSGA is the derivation. O is for oxalic. It will give you the order that how the CH2 length is increases. So oxalic, then there is the malonic, then there is the succinic, then there is the glutaric, and at the last there is adipic acid. So you can remember this OMSGA, right? So OMSGA is giving you that you just keep in your mind that one of the simplest example of the dioic acid that you are not having any of the CH2 between these two carboxyl sides. So this is with the 0 CH2. So this is the ethane dioic acid, and its common name is oxalic acid. So you have used in a lot of your titration experiments and most of your teaching labs. So another one is the 1 CH2. So this is the propane dioic acid. This is the malonic acid. And if we keep on extending the CH2, so here you can see this is a 2 CH2. So this is the butane dioic acid. This is succinic acid. Then there are the 3 CH2. This is the pentane dioic acid, glutaric acid. How this is pentane dioic acid? Because this is the 5-membered chain in total, and they are the 2 carboxyl side on both corners. So this is the 1, 2, 3, 4, and 5. Now this is the adipic acid. It is its common name, and its IUPAC name is hexane dioic acid. So this is the 1, 2, 3, 4, 5, and 6. So you may ask that why we are not mentioning the position of the carboxylic acid. So I have told you that the carboxyl side will share the corner or extreme or terminus of the molecule. So then this is understood that they are at the both corners of the molecule. So there is no need to mention that one. Otherwise, if you write, even then that is fine, that you can write it 1 and 6 hexene dioic acid. So even then that is fine. Now, another case is the cyclic carboxylic acid, when there is a ring in a structure. So for this, you will name that cycle, whatever the carbon chain is making that one. And if there is any of the double bond or any of the substitution, you will name as we have discussed in our previous slides or refer to the other previous lectures. So here in this case, this is the 6-membered cyclic structure, and there is the carboxylate side, right? So we will always start numbering from the carbon which is having that carboxylic group, right? So 1 is this. So I may move from this 1, 2, 3, but the right direction is this one, because here we have another functionality for which we have to assign this the lowest number. And if I go to this direction, so then that will get the 1, 2, 3, 4, 5, and 6. Then that double bond will be mentioned between the 5 and 6. That is not according to the IUPAC rules. So we have to assign any substitution, any other functionality as the lowest number. So this is a 1, 2, and 3. And for the double and triple bond, we always write the first carbon from which the double bond is started. Or you can say we will write the lowest number of the carbon which is involved in the double bonding. So this is the 2 for the position of the double bond, that this is between carbon 2 and the carbon 3. This is cyclo because this is in a ring structure. If I don't write the cyclo, so it means I'm giving you the idea that it is only the aliphatic and an open chain structure. So then you are not able to draw its correct structure. So cyclohexene carboxylic acid is its name. Now this is the 5-member ring structure, and on a both side it has the carboxylic group. So if you just look at this, one is the solid line and one is the dash line. This is the wedge line. So wedge is always to show that this functionality or this group is on towards the viewer, and this is on to backward, right, in the spatial rearrangement. So they are in opposite direction. So there's one is facing the viewer, or this is the forward, and this is on the backward direction. So it means they are opposite. So we will write the trans. And now 1, 2, and 3, right? Again, we will not go to this direction 1, 2, 3, 4, because now this will get the higher number. So we have to assign the substitutions lower number. We have to go to that direction where we can accommodate most of our substitutions with the lowest numbers. So 1, 2, 3, 4, and 5. So 1 and the third position, here there are the carboxylate groups, right? So this is the cyclopentane dicarboxylic acid. So here you can see that we have mentioned the positions of both carboxyl side, because this was a cyclic structure. So that could be totally an opposite. That could be just next to this one, because this was not opposite. This was not open structure that we assume that they are sharing the both extreme ends as we have did in the previous slide. So we are mentioning the 1,3 cyclopentane dicarboxylic acid. Now this one is about the aromatic carboxylic acid. So aromatic carboxylic acid are those carboxylic acids which are the derivatives of the benzene, and they have the benzene ring attached to that one. So for this, we will use the benzene, and this is IUPAC accepted, IUPAC approved naming, that we will use the benzene or the benzoic acid for naming these compounds. So the simplest of the aromatic carboxylic acid is that we have the benzene ring and there is the one carboxyl group. So this is the benzoic acid. And now if, though we can write it as the 1,3,5 cyclohexatriene on oic acid, methanoic acid, but because that is too complex and messy, so this has make the task easier. So IUPAC has accepted that benzoic acid mutation, so we can name the aromatic carboxylic acid on that frame or on with that reference. So this is the benzoic acid, and if we put any of the substitution on any side there, so there is the OH group. So how we can write it? This is the 1 and 2. So this is the 2-hydroxy benzoic acid, because this is the hydroxy substitution which is added it on the basic structure of the benzoic acid, right? So just remember, firstly with the benzoic acid, a benzene ring with the carboxyl group. So whatever the substitution we will put, so we will name that accordingly. So now this is the case where we have the 2 carboxyl side. So again, this is the 1, 2, because that could be at the 1 and 4th position in cyclic structures, that could be anywhere. So here this is mandatory that you can mention, you have to mention the position of both carboxyl groups. So this is at the 1, and adjacent to this carbon, very next, there is another carboxyl group. So this is a 1 and 2 benzene dicarboxylic acid. So we are not using the oic acid here because benzene itself is covering this structure. So we are not including that parent chain. So we are just mentioning that carboxyl group. So we will write the carboxylic acid here. Now another example is that they are exactly opposite to each other, right? And at the 180 angle. So this is the 1 and the 4th para to each other. So this is the 1,4 benzene dicarboxylic acid. I hope you got the idea how you can name the carboxylic acid, if they are aliphatic, if they are cyclic, if they are aromatic one, and if you have the OH, NH2 or carbonyl substitution, so what would be the preference? So do remember that carboxylic acid gets the preference over all of the functional groups in the organic compounds. And the second, you have seen that how you can name if the carboxylic acid has another carboxyl group. So you will use the terminology dioic acid, you will use the suffix dioic acid in case of the aliphatic. So, but in case of the aromatic one, you will use the dicarboxylic acid. So at the end, I have given you a task. So in the first question, they are the 3 structures which has given to you. So you have to write the IUPAC name, explaining wherever there is the stereo chemistry involved, where there is the cis and trans conformation. So you have to write that one. The second question is that you have to draw the structure of these compounds. I have given their name, IUPAC name. So you can just write their correct structure and you have to submit that on Moodle. So if you have any query, you are free to ask. Don't hesitate to comment. And I would appreciate if you like and subscribe the channel if you are enjoying the lectures and you are getting the interesting stuff from this. Take care. Bye-bye.